Okay, so the very first step on this problem and all other problems is solve for the support reactions. I would like to not do that now because that pretty much wastes your guys' time at this point, I believe. So can somebody give me what they got for the support reactions? Oh, it's on your homework?
Yeah.
I'm sure somebody still got their homework with you. Got it, KB? What's AY?
AY, I got 72.
72?
Yeah, the same with BY.
Kip? And BY is also 72. Great, and then we have our distributed loads, which go up like this, and down, and up, and down. Okay, so there is my free body diagram. I don't think there's no moments or anything like that. So let's do the shear diagram. We're going to do it in two different ways. The first way is just by finding areas. So, Molly, your question was about section diagrams. When you're doing the relationships like we're doing now, the only thing that you need to do is draw the full free body diagram like that, not the section ones. Can you draw the section ones? Sure. And you can solve them that way, but it's not necessary when you're doing it this way. So we're going to start with shear, and that's going to be in kip. So I want to make sure I keep my units. Where do we start? 0. We start at 0, and the reason that we start at 0 is because there's no point load on the left-hand side. Then we're going to change. We're going to use the relationship that says the change in shear is equal to the area under the loading function, dx. That is both a relationship that we can use the words for and a mathematical equation. So how do we use the words for it? Well, this is change in shear, and this is area under curve. So if I were to color this red area over here, we can find that red area. That red area would be 1/2 base times height, which is 1/2 times 8 times 9, where this is 9 feet. And what is that, like 28? So I'm just going to call this red area 1 equals 1/2 times 8 kip per foot times 9 feet is going to be equal to 36. So I was way off. 36 kip. That means that between those 2 points, the shear is going to change, and it's going to increase or decrease. Decrease, good. It's going to go down because those arrows are pointed down. That can be confusing to some. Keep in mind that I could just as easily have drawn this exact same loading like this. Right?
Can we do that on the off?
Sure. It's the same thing. Drawing it on top of the beam or below the beam, it's the same idea. And you can see that we should expect a negative slope for our loading, not a positive slope. Okay, so now we know that we're going to go down, and we're going to go down 36. So I'm going to go down here, I'm going to say, at this point, we're going to be at negative 36 kip. But how we get there, we have to look at it. What's my initial slope? My initial slope is 0, because my loading starts at 0, right? So my initial slope is 0. So I'm just going to put a little dashed line that shows my slope. Then when I get to 9, where 9 is this distance here, when I get to 9, what's my slope? Negative 8. Very good. My slope would be negative 8, so it looks like something like that. So then I connect those two slopes, and I know I'm going to have a concave down parabola. Does that make sense? Okay, then what happens? Jumps up 32. So I'm going to positive 36 now. I'm going to be way up here. Or 72, sorry, not 32. I'm going to be at positive 36 kip. Okay, then what happens? I'm going to go down again, and I know how far I'm going to go down because that's the same triangle. I know I'm going to go down 36. I'm going to go back to 0. What's my initial slope? Negative 8. What's my final slope? 0. So it's going to look like this.
The two endpoints, is that always good? Because I like the way you're doing it.
Yeah, that always works. The equation that we're using is dv dx equals wx.
I always have
The slope of shear equals loading. What were you saying?
I never know, I can usually tell that it's, I guess I always think that it's a linear or parabolic or cubic, but I never know which way it opens.
Yep. Little tiny dashes for your slope will help with that. Then you can kind of picture it. Okay, once we get down to there, what happens? Yeah, we're going down again, and we're going down 36 again, right? So it's a repeat, exactly. It looks just like this. We're starting at 0, little slope of 0. We get over here, we're going to have a slope of negative 8, so we know it's going to go like that. It's going to jump back all the way up to here, and it's going to do the exact same thing to here. That right in the middle, this would be 18. This is 9. This is 27 and 36. Okay, any questions about how I got that? Okay, now moment. When we get to moment, things get a little bit tricky. We know we're going to start at 0. So we're going to start at 0, but then we have to go down this area, which is, how are we going to find that area? That's a parabola, right? It's more challenging. So what we're going to do is we're actually going to go back up to the top, and we're going to use these equations more rigorously. So I don't think I need this picture anymore, so why don't I give myself some more room? Now what we need to do is we need to come up with equations for our wx. We're going to start at the beginning, and we're going to use this mathematical equation. Instead of using it as a relationship, we use it as an equation. So we need our wx. So I'm going to start at 0 and go till 9. So for 0, 0 is less than or equal to x, which is less than 9. I didn't do the equal because we have a discontinuity at 9. Not a big deal, but just little details. For that distance, I need a wx. How do I find it? The easiest way, the no-fail way, is to come up with 2 points. My first point would be 0, 0. What's my second point? 9, negative 8. You could either put 9, negative 8 or 9, 8, but you have to know what you're doing, right? If you put 9, negative 8, you've already put that negative in there, and if you remember our equation where we say the integral of dv equals the integral of wx dx, there's a negative sign here. That's the equation. It has a negative in it. Why does it have a negative in it? Because we're pointing down. If we already put that negative here, this goes away. You only put it in once. So if I'm going to do negative 8, I'm going to make that go away. Now that I have those 2 points, I like point slope form because then I only have to remember one thing. Don't have to remember more than one. What is point slope form? Y minus y1 equals y2 minus y1 over x2 minus x1 times x minus x1. Plug those in. Y minus 0 equals negative 8 minus 0 over 9 minus 0 times x minus 0. So y, which is really my wx, is equal to negative 8/9 x. Okay, this can be confusing. What does the plot of negative 8/9 x look like? Does it go up or down? It goes down. What does the plot of my loading function look like over here? It goes up, right? Confusing, right? Why? Why is it like that? Because the negative direction. I put the negative direction by putting in -8, right? As I said before, I could just as easily have taken that loading and drawn it like this. If I erase this top part and I draw the loading like this, isn't that exactly the same problem? And it's going down, right? The problem is, if you look at this on an XY plot, it's going to look like that, because you start at 0 and you start going negative. When we put our loading, we often draw it the other way, whereas it looks like it's going up, but the arrows are pointing down. Don't let yourself get confused. If you do it on the bottom, yeah. Yeah. Okay, let's go ahead and work through, and now we're going to get the equation for that parabola. So I now have my wx equals -8/9 x, and I'm going to use the equation. The integral of dv is equal to the integral of wx dx. Notice I took the negative out because I already incorporated it. Now we just need limits of integration. We're going to go from our initial v0 to v, and we're going to go from x equals 0 to x. The reason we go from 0 to x is because we're starting right here at 0. We're starting between 0 and 9. I'll show you how that changes on the next interval. So then we have v minus 0 is equal to the integral of -8/9 x from 0 to x dx. We're going to have -8/9 x squared over 2 minus 0. Is that 1/4 equals -4/9 x squared. That is the equation of this right here. If we plug in 9, what do we get? -36. So we're good, right? Now the nice part is we can go right down to moment. And we can say that my shear, I need more space, so I'm just going to write my shear up here. Shear of x equals -4x squared over 9. I'm going to erase the rest of what I have because that was all just to help me find the shear. You guys ready for that?
That's for a very specific region of the graph, though. Is that
Correct.
important to highlight?
Yes, absolutely. And we're going to do it for every portion of the graph. Okay? So, and I did highlight it. See at the top here? It's written very clearly. So for that portion of the graph, we can now use the equation, the integral dm equals the integral of shear dx. This is going to be from the initial m at 0 to m. This is going to be from the initial x, which is 0, to x. So that's going to be m minus 0, because m starts at 0. There's no couple moment at x equals 0. Is going to be equal to the integral of shear, which is -4x squared over 9 dx from 0 to x. So we get -4x cubed over 27. We now have an equation for moment. -4x cubed over 27. So what's it going to be at 9? Well, we plug 9 in. So the moment at 9 equals -4 times 9 cubed over 27. -108. -108, excuse me. So we're going to be down here at -108. What's our initial slope? 0. And what's our final slope? -36. Very negative, right? So I'm going to have this plot like that. Now that is a cubic, and it might look a little different. You can go ahead and plot it on your calculator if you want to see what it looks like. But remember, cubics only look different than parabolas in the inflection point. If you're not plotting the inflection point, they basically look the same. Questions about what I did there? Okay, we're going to just store this up here. We're going to say that for that, shear is equal to negative 4x squared over 9, and moment is equal to negative 4x cubed over 27. So we have those two for 0, between 0 and 9. Now we're going to do for 9 is less than or equal to x, which is, 9 is less than x, which is less than 18. We can only go to those because we have discontinuities between them. For that, we know we can come up with a wx. How are we going to come up with a wx? Point-slope form, exactly the same way. What's our first point? 9, negative 8. And our second point? 18, 0. Good. Y minus y1 equals y2 minus y1 over x2 minus x1 times x minus x1. I'm going to choose this as my y1 because I get a 0, and that'll make my math easier. That's okay. We can choose either one as 1. So being y minus 0 equals negative 8 minus 0 over 9 minus 18. Sure. Why not?
Is it not like a vector? It's not like pointing one direction?
When you're finding the slope through two lines, you have either one point or the other as your first point. It doesn't matter which one you pick. You have to stay consistent here, though. Like I couldn't put x minus 9. I have to be x minus 18 because I picked that second point as my x1, y1. If you want to see it, let's do it both. X minus negative 8 equals 0 minus negative 8 over 18 minus 9 times x minus 9.
Oh, maybe that's an advantage of point slope form instead of mx plus b.
Yes.
Yeah, oh,
Yeah.
Point slope form is cool then. Okay, got it.
What I like about it is you only have to remember one thing
Yeah.
if it's point slope form.
Okay, thank you.
Mm-hmm. Okay, so then we solve for this and get, in this case, wx. It's not really y. I just called it y, so we recognize point slope form. That's going to be equal to, it looks like, negative 8 over negative 9. So that's 8/9 x minus 8/9 times 18, which is just 16, right? Yeah. So wx is equal to 8/9 x minus 16. We have a positive slope instead of a negative slope. Hopefully that'll make sense if I erase this up here and actually draw it on the bottom. Starting off at negative 8, we're going to 0. We would expect a positive slope. Okay, any questions about that? Okay, so I'm going to erase point slope form and put my wx up here. My wx equals 8/9 x minus 16. Now I'm going to say integral dv equals integral wx dx. Now here's where things get tricky and where you have to be very detailed. If you want, you can do a plus c. I don't like the plus c. What do I mean by plus c? You could do this integral with no limits of integration, and then you can, at the end, just put plus c and plug in 2 points. That will work. I don't like to do that. What I prefer is putting in the correct limits of integration, because it's just more rigorous, and it always gets you the right answer. What are my correct limits of integration? Where I'm just going between x equals 9 and x equals 18. What is my initial shear? No. Yeah, at x equals 9, what is shear equal to? 36, very good. So I'd put 36 here.
Even though that's like a discontinuity?
Yes, because we're going to the right side of that discontinuity, not the left side. We've already done the left side. That was we have it written right there in the corner. It's tucked away, right?
Okay.
Now we're skipping over the discontinuity, and we're now on the right side of it.
Okay.
No longer discontinuity. We're just at 36, and we're going to continue the plot from there.
Oh, because we wouldn't do that on the
We have gone through the time warp of the discontinuity, right? We did before it. We went through the time warp, and now we're continuing. What?
We went to 36 on the second integral though?
No, because 36 is the value of shear. How you know what you're putting on is always look at your element of your integration element. It says dv here, right? So we have to have limits in terms of v. And shear starts at 36. No. Well, will it end at 0? Yes. But we want an equation for it. We don't just want a single number. So we're going to do from 36 to v. So we can get an equation for it. Exactly. And we're going to do the same thing for x. What's our initial x? It's not 0 anymore.
Here's where I would have put like 9.1 because I have 9 for discontinuity, but it keeps playing at 9.
Yes, we're to the right of 9, so it's 9.0000000000000. You got it. Okay. To x, because we want x in there as well. Then we do this integration. We get v minus 36 on the left-hand side. That's going to be equal to the integral from 9 to x of wx, which is 8/9 x minus 16 dx. So shear minus 36 equals 8x squared over 18 minus 16x from 9 to x. So we get shear minus 36 equals 8x squared over 18 minus 16x. That's with me plugging in x. And then it's minus, we plug in 9 for all of those, 8 times 9 squared over 18 minus 16 times 9. Shear is equal to so that's negative 108, but we got another negative, so that's positive 108 minus 30 or plus 36, 144. Okay, so we now have the equation for shear. What is that equation? It's given right here. We can check it, right? We can plug in x equals 0. If we plug in, or x equals 9. If we plug in x equals 9, we should get 36, which it looks like we do. If we plug x equals 18, we should get 0. All right, so we can check that and make sure that it's right. So I'm going to put this up here now, kind of tuck it away. For 9 is less than or equal to x, which is less than or equal, well, sorry.
So you plugged in both the endpoints, right? Is that what you said you did?
Yes,
Okay.
to check them,
Okay.
just to check your work. Very good. So for that, my wx equals 8/9 x minus 16. My shear of x equals 8x squared over 18 minus 16x plus 144. Now is where the useful part comes in. All we've done so far is gotten an equation for a line we already graphed. Not very useful. But we need to find moment. So now to find moment, we're going to say the next equation is the integral of moment dm equals the integral of shear dx. We need our limits of integration. Where am I going to start on the left-hand side? There's always two things you check. The first thing you check is where did I end on the last portion of my moment? I ended at negative 108. The second thing you check is there any discontinuities? There's not, right? There's no couple moment acting at x equals 9. There's discontinuity in shear, but there's nothing in moment. So that means we're still at negative 108. So we're going to put in negative 108 here to m, and then on the right-hand side we go from 9 to x and perform the integration again. M plus 108 equals the integral of 8x squared over 18 minus 16x plus 144 dx from 9 to x. Plus 108 equals 8x cubed over 3 times 18 minus 16 8x squared plus 144x from 9 to x. You guys get the idea, right? So now I would plug all that stuff in. I would get m equals 8x cubed over 54 27. I could make that 4/27. 4/27 minus 8x squared plus 144x minus 8 times 9 cubed over 54 minus 8 times 9 squared plus 144 times 9 minus 108. Okay, so we got ourselves an equation for the moment between 9 and 18. Then we can plot it. Really, all we need to plot it is we need to plug in 18. So if we plug in 18, we get 4 times 18 cubed divided by 27. Zero. What a surprise. So then we can plot it and we can say, well, we're going to start at negative 108. We're going to have a slope of positive 36, which is going up like that. We're going to end at a slope of 0. Then it just repeats. And I've said this in class before, but basically if you have a linear load, then you're going to have a quadratic shear and a cubic moment. There's no easy way to find the area of a quadratic. So you have to do calculus to find it. If you have a constant load or a zero load or point loads, then you're not going to need to do the calculus. There's also ways you can go from one side, from both sides to find it. But those are all shortcuts. This is the real math. This is when you find the actual equations. And it is critical, because I could very easily put a problem on the exam that has two loads that are not constant, or that are linear loads, and then you need the calculus.